Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Zamir Ikhwan bin BAHARUDDIN. Okay, today our group will present the project report CNC milling machine. We are from section 03P, undergarden lecturer Dr. Rosmazi bin Rosli. Okay, first of all, I will introduce our group. We have Muhammad SYUAIB bin SUHAIMI, Muhammad RAIS, SOLIEHIN, Muhammad AMIRUL IKHMAL, and me, Muhammad Zamir Ikhwan bin BAHARUDDIN. Okay, we go. Okay, I will present for part 2. Okay, for part 2 is finding case study and modeling the system. Okay, our group has selected milling machine as a system for the project, which we want to model using MATLAB Simulink. The milling machine is a mechanical device that is used to remove metal. Milling can be distinguished by its process: face milling and peripheral milling are the two most used milling technique. For different milling procedure, different mill cutter are utilized. The cutter are frequently distinguished by the number of teeth or flute they have. Okay, this milling machine with more than 2 degrees of freedom, as we know. Okay, and electrical power source is typically used to power milling machine. Okay, there are some parameters that we can handle in the milling machine process, including cutting speed, cutting force, and cutting depth. For example, okay, our group were involved in creating a milling machine model in this project, that the cutting force is the parameter to be handled. Okay, we go to next is define the system input, output, subsystem, and all the signal involved. Okay, this is the block diagram of the open loop of the system. Okay, in this block diagram have the input is the reference force, that is FR in Newton. The output is measure cutting force, FP, Newton. For the subsystem is the controller, CNC, feed, driver, motor, and amplifier and cutting process. And lastly, the signal for this block diagram of an open loop of this system is signal CNC machine. Next is the transfer function and the Laplace transformation. Okay, this is for the figure show the pre-simplified schematic diagram of the milling machine. Okay, this is the free body diagram for block diagram, and at the is the calculation, the Laplace. The input is data 2, and the input is T1, and from the calculation we get the Laplace is equal to data 2 per T1 equal to N2 over N1 times JE S square plus DE times S plus K. This is the Laplace transfer function for this our project. Okay, we go to next is complete block diagram in Simulink. Okay, for the figure show, this is the complete block diagram in Simulink. Okay, we have step, transfer function, and gain, function gain, scope, and CMOUT. Next is this is our coding for this project. The parameter for this system is B is equal to 20, N equal to 900, KC equal to 2450, KN equal to 1, AP equal to 2, P equal to 4, M equal to 0.9, KE equal to 2, N equal to 0. Okay. Next is a preliminary evaluation of our system by using the step input, like in example in part 1. Okay, this is the result. Figure 1, time plot signal. In this plot have cutting force and desired cutting force, and this is also the result in Simulink. Okay, when the cutting force is applied from the parameter indicated above, the required cutting force signal produce a transitory response. However, based on the graph above, this signal require a short time to attain the required output or steady state response. Okay, next we go to the system. The system can be controlled in a closed loop. Okay, this is the block diagram for closed loop, and the input you have reference, control, CNC, feed driver, motor and amplifier, cutting process, output, sensor. This is the block diagram for closed loop. Okay, that's all from me. For the part 3, the SYUAIB will present. That's all from me. Thank you.
Assalamualaikum. My name is MUHAMAD bin SUHAIMI, metric number MA18113. I will present on the part 3 evaluation of time response and performance of the system. On the question 1, time response using Simulink. So we create the block diagram that we choose in part 2 using transfer function in Simulink. So this is our block diagram. This is our M script that we write to run in our Simulink model. Next, we use a step function with an amplitude of 1 and we run the model again. Then we obtain the time series graph. The elapsed time is 1.182344 seconds because we use a step function with an amplitude of 1, so the graph is more slanted than previous. So the effect of varying each parameter of our system on the time response is that the lower the amplitude and the lower the time response, so causing the graph to becoming more inclinations. So to improve the performance, we must raise the amplitude. And next, for the question 2, time response performance analysis using linear system analyzer. So we create a new M file script, then we name it as a part 3 and save it. After that, we enter the parameter of our chosen system in part 2, and then we create the transfer function using tf command. Also that we run the script, so MATLAB will register our transfer functions and the command window will prompt on our transfer functions. So this our step response in LTI viewer. And last, we identify all the performance characteristics of our system by finding the settling time, rise time, steady state value, and peak response. For our systems, all of the peak performance settle at more than 500 seconds.
Assalamualaikum warahmatullahi wabarakatuh. My name is AMIRUL bin Muhammad ZULMI. My ID number is MA181. So today I want to present about for part 4 for our project for the title is stability analysis, poles and road criterion. So for the question 1, pole zero map. First is in the same criteria that you have used in part 3, identify the location of the pole of your system by right click, plot type, pole over 0, figure 10. So I using a MATLAB, and we got this graph, pole zero map using LTI viewer. Next we go to number 2, show the pole zero map and describe the stability of the system from it. So if its output is under control, system is said to be stable, otherwise it is said to be unstable. A stable system produces a bounded outputs for a given bounded input. The following figure show the response of such a stable system. So there is a stable system from the zero pole map. For the question 2, for RS criterion, first this question is write manually RS criterion table. So we have a equation 400 over s square plus 20s plus 400, and we I make a width table, and we find for B1 we got this one by using formula. I got 400 for s naught, and for B2 I got 0. So from the calculation of the RS criteria table above, we have find that the resulting system is unstable because the values obtained from the table above are all positive value, and if there is a negative value, it is likely that the resulting of system is unstable. So we can say that the system is in a stable condition by looking at the result of the width table above. The next question is for number 3. We compare both method that you have used, pole zero map and RS criterion. For the first point, compare between pole zero map and RS criterion. So we investigate that RS criterion is much faster and less in error than pole zero map. This is because RS criterion result will directly point out the system is either stable or not, while pole zero map we must sketch the graph and then do the interpretation from it. Next point is the advantage of pole zero map is we can track the system stability when we change parameters in the system, which lesser effort than using the RS criterion, but we must do not need to read whole calculation and only depend the visual by our eyes. So I think that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is RAIS bin MOIDEEN, metric number MA18106. Today I will talk about the chapter 5, part 5 from our project, which is the steady state error performance. Okay, so this is the So first of all, we need to know what is steady state error. So the difference between the input and the output of a system in the limit as time approaches infinity is defined as a steady state error. So when the response has reached a steady state, for example, when the response has reached a steady state, so that is called a steady state error. So the steady state error is affected by both the type of input and the system type. The type of input is like the step, the ramp, and etc. And the system type is like 0, 1, or 2. So a steady state error is a property of a linear system input or output response. So a good control system will in general have a low steady state error. So as you can see here in this figure here, we use a few signs here, and the main thing here is the transfer function our transfer function is 400 over x squared plus 20s plus 400. So that is our transfer function for this Simulink model. So this is our time response graph for the simulation. We just need to click the scope just now, the model scope, and double click, so you will get this one. So only for unity feedback system can we find the steady state error. As a result, we must convert the non-unity feedback system to unity feedback system. So as you can see here, this is the graph that we got from the simulation, from the model Simulink that we did above. So that's all for our part 5. Thank you.
My name is SULAIHUDIN. My metric ID is MA18135. Okay, so part 6, root locus. Root locus analysis is a graphical method for examining how the roots of a system change with variation of a certain system parameter, commonly again with a feedback system. Transfer function parameter equation: SYS equal to 400 per s square plus 20s plus 400. Okay, figure 6.1 show the model script. Okay, we put the coding like this figure to get the equation of continuous time transfer function. Okay, this is figure 6.2 show the root local diagram that we get from the script. Figure 6.3 show the result of the graph. Okay, so for the first point at the top, system that we use is SYS. Gain is 0. Pole is minus 10 plus 17.3 I. Damping is 0.5. Overshoot is 16.3% and the frequency is 20 radian per second. And the second point at the bottom, system that we use is SYS. Gain is 0.0498. The pole is minus 7 minus 17.9 I. The damping is 0.488. The overshoot is 17.3% and the frequency is 20.5 radian per second.
So I will continue with the part 7, PID controller. So as a result, we decided to improve our response system in terms of a steady state error. To improve the system, we use a PID controller with proportional control. PID is control solve the overshoot and ringing problems, but it does not solve the steady state error. It is possible to eliminate using low gain by including an integral term. Proportional integral derivative controlling PID is feedback-based control loop mechanism that is widely used in industrial control system and other applications and required continuously module control. So this is our coding for our PID control. So this figure shows our PID control coding. And as you can see there, line 17 until 19, we input the value for KP, KI, and KD. So we keep changing to have a better graph. So this with KP20 and KD, we have KP20 and KD20. This graph show here is the overshoot. This graph shows that there is an overshoot, that the setting time increases. As a result, this system is unstable. To reduce the overshoot, we increase the KD. So So as you can see here, after the KD is increased, we can see the overshoot gradually decreasing and the rise time slightly increasing. So in order to reduce the overshoot, we increase the value of KD. Same goes to the next graph. So without the use of KI, the graph enter a stable steady state and the response is less than 0.2% and of its final value. So we have a better graph here for our PD controller. So we managed to get this graph. So I think that's all for our PD controller. Alright, that's all. So to conclude, for a conclusion, we learned how to design a control system using MATLAB software. As a result of this project, we developed the system model through Simulink based on the transfer function of the chosen system. So which is the miling system lah, which is the miling machine we use. So using MATLAB software, we were able to analyze and evaluate the system design such as poles and zeros, root locus, and system stability. The PID controller was used in the miling machine system to improve the system response in terms of steady state error, overshoot, oscillation, rise time, and settling time. So we hope to put this knowledge to use in our future. That's all from me and my teammates. Thank you very much.